Assalamualaikum and good morning everyone. So today our group would like to present Titration, Basic Analytical Chemistry. But before we go further, I would like to introduce my team. First we have Nur Batrisha, we have Nur Shaliza Jamaluddin, we have Nur Safira Azmi, Nur Alia Shazza, and last but not least me, Muhammad Denish Imran. So to start things off, we look at the introduction of titration. First, what is exactly a titration? By definition, it is a quantitative analytical technique that we use to determine the exact unknown concentration of a substance. We do this by reacting it with a reagent that has a known concentration. The core principle behind this technique is a precise chemical reaction between these two solutions, the known and the unknown. As we slowly add one to another, we look for exact moment the reaction completes, which we call the stoichiometric equivalent point. Finding this volume allows us to mathematically calculate the precise molarity of our analytes. Because this method is so accurate, it has a vital real-world application across global industry for quality assurance. For example, it is used to monitor food acidity for taste and safety, to test drug purity in pharmaceutical, and to detect harmful pollutants in our water system. Let's look at a practical example of how this works in laboratory setting with our experiment, the determination of percent content of acetic acid in vinegar. To give you some background, household vinegar is essentially a diluted solution of acetic acid, CH3COOH. For standard commercial vinegar, it typically needs to contain an acetic acid concentration of about 4% to 6%. To verify this exact concentration, we use the titration method. Because acetic acid is an acid, we can determine its content by reacting it with a standard solution of a base, in this case, sodium hydroxide. For our experiment, our main goal is to determine the acetic acid content of commercial vinegar. To ensure our results are highly accurate, we titrate this vinegar sample using an NaOH solution that has already been precisely standardized beforehand using a secondary standard solution of hydrochloric acid.
Hi everyone, so today I will explain the theory behind the determination of acetic acid in vinegar. This experiment uses an acid-base titration to determine the percentage content of acetic acid in a vinegar sample. As shown in the chemical equation, acetic acid reacts with the sodium hydroxide to produce sodium acetate and water. So from this balanced equation, we can see that the mole ratio between acetic acid and sodium hydroxide is 1 to 1. This means that 1 mole of acetic acid reacts completely with 1 mole of sodium hydroxide. In this experiment, vinegar is the analyte because it contains acetic acid, while sodium hydroxide is used as the standard solution or titrant because its concentration is already known. Furthermore, during the titration, sodium hydroxide is added slowly to the vinegar until the neutralization reaction is complete. By measuring the volume of sodium hydroxide used, we can determine the amount of concentration of acetic acid present in the vinegar. Next is the neutralization process and the endpoint of the titration. To identify when the reaction is complete, phenolphthalein is used as the indicator. Phenolphthalein is colorless in acidic solution but turns pale pink in basic solution. So at the beginning of the experiment, the vinegar solution is acidic, so it remains colorless. And as sodium hydroxide is added, it gradually neutralizes the acetic acid, and the endpoint is reached when a permanent pale pink color appears and remains for about 30 seconds. This color change indicates that all the acetic acid has reacted with sodium hydroxide, and any additional sodium hydroxide makes the solution slightly alkaline. At this point, the volume of sodium hydroxide used is recorded because it will be used in the calculation of the percentage content of acetic acid. Finally, I will explain the calculation principle. The first step is to calculate the number of moles of sodium hydroxide using the equation of N equals to MV. Next, because the reaction has a 1-to-1 stoichiometric ratio, the number of moles of acetic acid is equal to the number of moles of sodium hydroxide. After that, we calculate the mass of acetic acid using the equation of mass equals the number of moles multiplied by molar mass. Finally, the percentage content of acetic acid is calculated by dividing the mass of acetic acid by the mass of the vinegar sample and multiplying by 100. So to conclude my explanation, this analysis is very important because it is widely used for quality control of vinegar product, ensuring that they meet food industry standard and that the labeled acetic acid concentration is accurate and reliable. That's all from me. Thank you.
Okay, we move to the next part, which is methodology. The objective of this experiment is to determine the content percent of acetic acid in vinegar. So this experiment is carried out using 250 ml of conical flask, 250 ml of volumetric flask, 100 ml of beaker, retard stand, burette, 20 ml of pipette, analytical balance, weighing board, white tile, glass rod, and lastly phytophthane. The chemical reagent that we'll use in this experiment is commercial vinegar, sodium hydroxide perlite, 0.1 molar of hydrochloric acid, phenolphthalein as indicator, and lastly distilled water. First thing first, we calculate the mass of sodium hydroxide perlite required to prepare 250 ml of 0.1 molar sodium hydroxide solution. The sodium hydroxide perlite are then weighed accurately using an analytical balance and a weighing board. Next, the sodium hydroxide perlite are then transferred into 100 ml of beaker. and then add about 50 ml of distilled water and stir slowly until all the sodium hydroxide pellet are completely dissolved. Next, using a filter funnel and glass rod, transfer the solution carefully into 250 ml of volumetric flask, and then rinse the beaker a few times and transfer the water into the volumetric flask. And then add distilled water up to 250 ml calibration mark. When it approaching 250 ml calibration mark, please use stopper to avoid excess. Next, by using a volumetric stopper, seal the volumetric flask and turn the flask upside down a few times to ensure the sodium hydroxide solution is completely mixed and homogeneous. Next, fill the burette with prepared sodium hydroxide solution and check to ensure there is no air bubbles. And then pipette 20 ml of 0.1 molar of hydrochloric acid into 250 ml conical flask, and then add 2 or 3 drops of phenolphthalein into the conical flask as indicator. And then titrate the hydrochloric acid in the conical flask with the sodium hydroxide from the burette slowly while shaking the flask until the indicator color change. And then repeat this titration 2 to 3 times and record all the reading in the table. So the last step is calculate the exact molarity of sodium hydroxide solution. So the next is determine the acetic acid in the vinegar. First of all, pipette 10 ml of commercial vinegar into 100 ml of volumetric flask, and then dilute it with distilled water until calibration mark. And put a stopper and turn the flask upside down until it completely mixed and homogeneous. And then pipette 20 ml of dilute vinegar into 250 ml of conical flask, and then add 2 to 3 drops of phenolphthalein in the conical flask as indicator. And then titrate the vinegar in the conical flask with the sodium hydroxide from the burette slowly while shaking the flask until the indicator color change. And then repeat step 2 and 3 2 more times, and then record the reading at the end point of the titration. The last step is calculate the W/V percentage of acetic acid in the commercial vinegar sample. That's all from me. Bye!
Next, I will explain the result obtained from acid-base titration experiment. For the rough titration, we got 10.5 ml, and for the 3 trial after that, we got 9.9, 9.8, and 10 ml. The results are very close to each other, showing that it is consistent and reliable. Therefore, the average volume of sodium hydroxide used is 9.9 ml. Using the average volume and the concentration of sodium hydroxide of 0.095 molar, the moles of sodium hydroxide was calculated using formula moles equal to molarity times volume, giving us the value of 9.405 times 10 to the power of negative 4 mole. Since the reaction between acetic acid and sodium hydroxide has a 1:1 mole ratio, then the moles of acetic acid in the vinegar sample is also 9.450 times 10 to the power of negative 4. Next, the mass of the acetic acid was determined by multiplying the number of moles by molar mass of acetic acid, which is 60 gram per mole, and this gives us a result of 0.05643 gram. Finally, the percentage of acetic acid in 2 ml vinegar sample was calculated. Using the formula mass of acetic acid divided by volume of sample used times 100, result obtained was 2.82% weight per volume. In conclusion, the concentration of acetic acid in vinegar sample was successfully determined by acid-base titration experiment. The consistent titration readings indicate a good precision, and the calculated acidity shows that the experiment was carried out successfully.
Alright, so to wrap everything up, the experiment was a success. We managed to measure the exact amount of acetic acid in the commercial vinegar sample using our acid-based titration method. Based on this video, there are 3 main things we want to take away from this video. First, about the method itself, using the standardized sodium hydroxide with the phenolphthalein indicator worked perfectly. It gave us a really clear visual endpoint to find the unknown concentration. Next, if we look at the actual number, we use an average of 9.9 ml of sodium hydroxide, which helped us calculate that there was about 0.05643 grams of acetic acid in the sample. That brings our final concentration to 2.82%. And finally, when it comes to how accurate the experiment was, this result actually fits right into the expected standard range for commercial vinegar. So, it showed that our lab procedure was reliable, consistent, and exactly the kind of test used in real-world quality control. And that's all from us. Thank you so much for listening, and we are happy to take any question you might have. Bye-bye!